What is reactance in AC circuit analysis? Imagine a circuit where the flow of electricity isn't just about resistance but also about how the circuit's components respond to changing currents and voltages. That's where reactance comes into play. Reactance is the opposition to alternating current in a circuit caused by inductors and capacitors. And like resistance, which turns electrical energy into heat, reactance temporarily stores energy in magnetic or electric fields and then releases it back into the circuit. This means reactance doesn't waste energy but influences how current and voltage behave together. Reactance is measured in ohms, just like resistance, and is symbolized by the letter X it arises from two main sources: inductive reactance and capacitive reactance. Inductive reactance happens because of inductors, which resist changes in current by creating a magnetic field. The faster the current changes, the stronger the magnetic field, and the higher the reactance. Its value increases with frequency and the size of the inductor, following the formula XL equals 2 times pi times the frequency in hertz times the inductance in henries. When inductive reactance is high, it causes the current to lag behind the voltage, meaning the current reaches its peak after the voltage does. Capacitive reactance comes from capacitors, which resist changes in voltage by storing electric charge. When the voltage across a capacitor changes, it either charges or discharges, resisting that change. As frequency increases or capacitance grows, capacitive reactance decreases. Its formula is Xc equals 1 divided by 2 times pi times the frequency in hertz times the capacitance in farads. When capacitive reactance is high, the current leads the voltage, reaching its maximum before the voltage does. The total reactance in a circuit is the difference between the inductive and capacitive reactances. It is calculated as X equals XL minus XC. This total reactance determines whether the current leads or lags the voltage and affects the overall impedance of the circuit. Impedance combines resistance and reactance to describe how a circuit resists current flow in AC conditions. Reactance plays a key role in many electrical systems. It influences phase relationships between voltage and current, affects resonance where reactances cancel out, and impacts power flow. At a specific frequency called the resonant frequency, the inductive and capacitive reactances are equal and cancel each other out. This results in the lowest total reactance and the highest current flow. Understanding reactance helps engineers design filters, oscillators, and power systems where controlling phase and frequency response is essential. When combined with resistance, reactance forms impedance, which fully describes how an AC circuit resists current.